Hello AP Chemistry and welcome to 16.8, the section where we tie together Ka and Kb. So your book goes through this derivation, but just to point it out one more time because it is really important and really essential to why we have the relationships that we do, right? So here we have a Ka equation for which we could write a Ka expression. Now how do I know that Ka is the right label for this? Right, a couple of reasons, right? So one, it produces hydronium ion, which means that this process is acidic, right? This is an acidic process where we increase the pH of the solution, right? So that's one clue, right? In addition, what we start with, right, ends up deprotonated, right? What we start with is deprotonated, meaning that this is an acid, right? And this is its conjugate base, yes? Right, so I know that Ka is the appropriate term for this process. Here, I've labeled this with a Kb. How do we know that Kb is appropriate for this process? Right, one, we have our hydroxide being produced, and I know that this is a base because here it is protonated, yes? That's really, really important that you can see those and understand why this is an acid dissociation expression, and this is a base dissociation, yes? Super important. Okay, so then, if we wanted to sum these reactions, right, what do we notice? Right, we end up with 2H2O gives us H3O plus OH minus. What is that? Ding, ding, ding. That is Kw, right? Which means that if I add these two things and I end up with Kw, that means Ka, no, that's not what I want to say. Ka times Kb equals Kw, right? Which, if we think back one problem, I know that the Kb for this is equal to 1.8 times 10 to negative 5. What's Kw equal? Right, 1 times 10 to negative 14th, right? Which means that if I know that Kb is 1.8 times 10 to negative 5th, and I know this is 1 times 10 to the negative 14th, I can actually solve for Ka. Yeah, does that make sense? Which kind of goes back to what we talked about at the beginning of the chapter about how if something is a certain amount of acidic, right, we can also know how basic it is, right? And this is that exact same thing, right? If I know how basic NH3 is, right, I also know how acidic NH4 is. So if this is approximately 10 to the 5th, this is 10 to the 14th, this has to be somewhere around 10 to the negative 9th-ish, right? Which is why if I have this pair, if I'm comparing NH3 versus ammonium, right, I know that this is more basic than this is acidic. Yeah? Does that make sense? Okay. So anyway, so this is what ties those together, right? So Ka times Kb always equals Kw for a pair, right? Wherein I'm talking about a pair of conjugates, right? So this is the ammonia-ammonium conjugate pair. Yes? All right. So I could not use that, for example, to compare like ammonia to water, right? Because that's not what we're talking about. All right. Just to sort of emphasize the related nature of this, right? So here if I have HF, which I know is a weak acid, 10 to the negative 4th-ish, right? Then its conjugate base would have a Kb of, right, 10 to the negative 11th-ish, right? Which means that HF would be about this strong of an acid. Fluoride would be about this basic. Yes? Likewise here, so we have acetic acid, right, versus the acetate ion, right? Carbonic acid versus the bicarbonate ion, right? So forth and so on. Yeah, does that make sense? Okay. Which means that from here on out, it is super duper important that we can look at these and make that connection, right? We can make the connection that here it's talking about NH4 acting as a base or as an acid. So if I only had the Kb information, I could figure out this piece, okay? All right, thank you for listening. Be good, and we will pick up here and take all of this and start talking about salts, right? Where we're going to just basically start applying everything that we've talked about so far in chapter 16. All right, thanks for listening. Be good, and I will see you soon. Bye.